Hello, welcome to my pipeline integrity video series. My name is Colin Scott. I'm a pipeline integrity engineer based out of Calgary, Alberta, up in Canada. Today we're going to be talking about some statistics behind decision making. This is something that we do all the time as pipeline integrity engineers. Sometimes we make some safe decisions and sometimes we make unsafe decisions. Sometimes we spend money that we should be spending and sometimes we spend money that we don't necessarily need to spend. So today I'm going to talk a little bit about how some statistics can influence your decision making. Specifically, I'm going to be talking about failure pressure model selection. When I talk about failure pressure models, I'm talking about things like ASME B31G or Rstring when you're doing some corrosion work, or perhaps CoreLAS or API 579 when you're doing cracking work. There are various pressure models that are available from the industry standards to choose. Some of you that have seen some of my other videos also know that I'm working on my own failure pressure model, which is called the gamma exponent model. So my questions to try and answer today are, what sorts of failure pressure models do you choose? When you choose your model, what is its accuracy? What is its precision? And then in the important things are, how does it affect your mitigation decisions? And how much is it potentially costing you? Typically, when we look at a flaw assessment, it's a relatively simple process. We either have an inspection that's been done by inline inspection tool, or we have an inspection that's been done by a field technician in the ditch. And what we'll do is we'll take the dimensions of that flaw and we'll try to predict the failure pressure of that flaw using a given model. Again, we can use CoreLAS for cracks, we can use ASME B31G for corrosion, whichever model seems to be appropriate. Now, what we'll typically do in the integrity world is we'll calculate the safety factor that's on that flaw. And here, when I say safety factor, I mean the predicted failure pressure using whichever model divided by the operating pressure. Now, if we find that the safety factor is below 1, then that basically means that we are predicting that that flaw could fail at the maximum operating pressure. And so we're going to have to come up with a mitigation program ASAP. And that's going to involve either dropping the pressure or doing an emergency dig. If we have a safety factor between 1 and 1.25, that means that we're probably going to think about some mitigation, but we're not necessarily going to do it under emergency scenario. We're probably going to put it on a dig list. That might be a 3-month dig list, a 6-month dig list, or whatever the pipeline operator's procedures require. In the United States, typically there's a 1.39 safety factor on their pipelines, but essentially it's the same sort of idea. Now, an important thing to think about is each one of the failure pressure models that are available have an accuracy and precision. And these are all determined by integrity engineers like myself that like to play with statistics and data and fit the various data that we've got to the various pressure models. Now, when I talk about accuracy, the accuracy is generally determined by calculating the average of the safety factors of the validation data set. So you have a validation data set, you calculate a predicted failure pressure, and you compare that to the measured failure pressure. So here, when I talk about safety factor, I mean the true measured failure pressure divided by the predicted failure pressure. And then we can also think about precision, where we calculate the standard deviation of all the safety factors for the validation data set. So I'm probably confusing you a little bit here because we have a safety factor on our calculation, and then we also have a safety factor that's on our model. And what I'm looking at today is looking at how those numbers are being compounded. So what I'm going to do is I'm going to start with a couple of simple examples just to show you how I'm setting up my plots. Hopefully you can follow the thinking. And then I'm going to jump into several examples. Again, these are hypothetical examples that I've just made up, but I'm actually using some true accuracy and precision data from various models that have been published around the industry. So here we have the simple plot that we'll be looking at. On the y-axis, we have the PDF, which is the probability density function. And in simple terms, that just tells you how tall your normal curve is. I've made the assumption that we've got normal distributions on all of these models. That's, strictly speaking, not necessarily correct. In some cases, there are researchers that will use log normal distributions or Gumbel distributions, Weibull distributions, various things. I'm simplifying everything here and assuming a normal distribution. On the x-axis, we have our safety factor, which is the first of the safety factors I talked about. So that's the predicted failure pressure divided by the maximum operating pressure. And you'll see that I've got three colored zones on my plot here. I've got the red zone off to the left, and that represents safety factors predicted for a flaw that are below 1, which means that we are really going to worry about having an immediate failure. I have a yellow zone, which is between a safety factor of 1 and 1.25, which means that we're probably going to put that flaw on our long dig list. And then to the right, I have a green section, which basically means our safety factor is over 1.25, and we're not going to worry about it right now, though we would do a remaining life assessment either through a corrosion growth rate or through a fatigue crack growth type calculation for a flaw. Now, when you look at what I've done here, I've actually got a hypothetical assessment point at 1.10, which would mean that if I had a flaw under this scenario, I would put that on my long dig list. But I know that my model is not exact. I know that in this case, my model has got an accuracy of 1.0, which I've got up there in the legend, and a precision, I've got 0.20 as my standard deviation. So what you see there is I've got a normal curve which represents what is the true failure pressure distribution, or more specifically, the true safety factor distribution associated with that calculation. Now, because of an accuracy of 1.0, that normal curve is centered exactly on my assessment point. But because I have a 20% standard deviation, I have a relatively wide normal curve, meaning that I can't entirely trust that calculation I've done. Now you'll see two extra numbers here, 31% and 23%. The 31% represents the area under that normal curve that is in the red zone, okay? So that means there's a 31% chance that my true safety factor on that flaw is actually in a very bad place, and I really should be digging up that flaw immediately or taking some other mitigative actions. On the right side, you'll see 23% chance in the green zone, meaning there's a 23% chance that the true safety factor on this flaw is actually above 125, and I really shouldn't be worrying about it at all. And of course, you can calculate the difference there is what 46% means that I've made a pretty good decision based on my flaw. Hopefully that's easy enough to follow. I don't think it's rocket science, though. Sometimes it takes a little bit of thinking to kind of wrap your head around the way I do things. So hopefully that makes sense to you. Now let's take another example where we've changed a little bit. Here we've got the same assessment data point at 1.10, so that's in the yellow zone, and we're going to put that flaw on our long dig list. But in this case, we have an accuracy of our model of 1.10, meaning that on average, that model is about 10% overly conservative, right? So that's represented by the normal curve being shifted to the right. In this case, we've got a better precision on our model. We've got a 10% standard deviation, which means that we have a taller and narrower normal curve. That means that we've got a lot more confidence in the calculation. Now, when we look at the areas in the red zone, we find that there's about a 2% chance that we're actually in a very bad place, which is an improvement. But you'll see that we've also increased our green zone up to about 34%, which means that with this particular model, we're being safer, which is good, but there's also a higher chance that we're spending some money unnecessarily. Hopefully that makes sense to you. It's something I've been playing around with for a little while, and this imagery seemed to work pretty well for me, so I'm hoping it also works for you. Now I'm going to be using some industry model validation statistics. So the numbers I'm going to give you are real, and you can actually go and find them to play this game by yourself. First of all, Yan et al. Model error assessment of burst capacity models for energy pipelines containing surface cracks. That's a very interesting paper that's in the International Journal of Pressure Vessels and Piping. So I'll be reporting some API 579 data from that. We've got Yan et al. Validating crack assessment models with in-surface and hydrotest failures. That's a paper that looks primarily at stress corrosion cracking models. That was presented IPC in 2018. Then we've got Karyawasam et al., the plausible profiles model, improved corrosion assessment models, which is work that was performed by PRCI. That plausible profiles p-squared model is essentially a refinement of the well-known Rstring model that's used for corrosion. And then I'll also be referencing some data that come out of some of my validation work on my gamma exponent model. You can find those through YouTube. There are 6 parts to my video series, and I'll be discussing some of the numbers in there. So our first plot, we're going to come up with a hypothetical situation where we have a crack-like flaw. We've got a calculated safety factor of 0.95, and usually if you found a safety factor of 0.95, you get pretty worried because that means that you are in danger of an imminent failure. Now, in this particular case, in this particular hypothetical case, I'm using the API 579 model, which according to Yan et al. Has got an accuracy of 1.35, and it's got a standard deviation of 26%. So what you see there is because of that enormous amount of conservatism, the normal curve, which represents the true failure pressure or the true safety factor on that flaw, is actually shifted pretty far to the right. But because there's a fairly poor precision, we've got a fairly wide normal curve. Now, in this particular example, there's about a 14% chance that we're acting appropriately and that we do need to worry about this flaw and go out and do an immediate dig or drop the pressure as soon as possible. But this also shows you that you've got about a 55% chance that this flaw is really not as serious as you think it is, and you can quite reasonably not worry about this right now. Though, as I mentioned before, you would do some sort of fatigue calculation to make sure that your remaining life was reasonable and you were going to catch this flaw in the event that it grew before your next inspection interval. When you stop and think about this, though, here's a situation where you would do a calculation and probably get into a bit of a panic when, in fact, there's more than a 50% chance that you can put your feet up and not worry too much about this right now. Let's hypothetically say that the crack was not a typical crack-like, but it was actually a stress corrosion crack, and that you were using the Corlass model, and specifically just using the simplification that you had a semi-elliptical flaw profile. Now, if you look at the Yan paper from 2018, you'll find that Corlass has an accuracy reported at 1.27, which is a little bit better than we saw before, and it's got a standard deviation of 21%. So you'll see that in that case, the normal curve has been shifted over to the left a little bit, which means that we've got a higher chance, a 16% chance that we're making the right decision, and we've got a lower chance in this case, 42% chance that we should not be worrying about this. So I think that that demonstrates fairly simply that going to the Corlass model for an SCC flaw in this particular case, even though it's a semi-elliptical assumption, is going to help you with your decision making relative to an API 579, both in terms of safety and in terms of not spending money unnecessarily. If you were really, really lucky and you had an inline inspection tool, or you had a very good field technician that could determine the stress corrosion cracking profile, you'd be able to use that profile with Corlass as well. And this would be a level 2 assessment. When you get to a level 2 assessment, you increase the accuracy of the model to 1.11 and the standard deviation to 15%, again, according to Yan's 2018 paper. And here you've made a better and better decision. The chance that you're making a good decision and should be acting immediately is up to 36%. And the chance that you're making a very expensive decision is down to 10%. So this really is a step in the right direction. Now, one of the models that will be familiar to a lot of us, or a lot of the viewers out there, is the Rstring model. And up until very recently, the Rstring model was probably considered the most refined model that was available to do corrosion assessments. Now, if you look at the actual data of the Rstring model, and you look at the accuracy and precision, according to recent PRCI work by Karyawasam, you'll find that the accuracy on the model is actually not as great as you would think it is. It's overly conservative by 30%. That's not my number. That was reported in a PRCI report. However, the precision on the model is quite good. It's reported as 10%. Now here we have a situation where we have an assessment point at 1.10. So that's a hypothetical corrosion flaw that we would put on our long dig list. But when we look at this curve, we say to ourselves, well, there's actually a slim to nothing chance that this particular flaw is an actual real problem that we need to dig immediately. So that's good. But there's also a 97% chance that we're digging up this flaw completely and utterly unnecessarily. Now, if you think about it, there are thousands and thousands of digs performed by the pipeline industry every year that are based on the Rstring model. And what we can tell from this is that there's a very significant proportion of them that are really being assessed really overly conservatively. And we should think really hard about whether we should be spending our money on those digs or whether we need to come up with a better idea. Now, one of the better ideas that has come up very recently is the p-squared, the plausible profile model that's been prepared by PRCI studies. Now, if you look at the p-squared model, it has an over-conservatism of 13%, and it has a very good precision of 7%. So if we take a look at that same flaw that we just saw with a safety factor of 1.10, we find that moving to a p-squared model is actually a step in the right direction. We still have a slim to nothing chance that it's a real problem flaw, and we've got about a 50-50 chance that this particular flaw should be on the dig list or should be disregarded. Now, although that this is a big improvement, one thing that's really interesting is that if you think about it, when you have an accuracy of 13% overly conservative, and you have a precision on that of 7%, from a statistical perspective, and I'll leave you to do the mathematics yourself, but from a statistical perspective, this model has actually demonstrated itself to be inaccurate. Although it's one of the most refined models available, and probably the most refined model that's available in the industry standards, it has actually mathematically can be proven to be inaccurate. So that's something we should think about. Now, I mentioned that I was working on a model of my own, one that I call the gamma exponent model. And I've got my own version of the gamma exponent model, which I call the ELM. And it's an algorithm which is similar to Rstring and similar to p-squared. And I've managed to achieve an accuracy of 1.01, and I've achieved a standard deviation of 8%. So if we take that same flaw over again and take a look at it, we find that there's a very good chance, in this particular case, an 88% chance, that putting that flaw on the long dig list was the correct idea. So we've got a lot more confidence in what we're doing. Now, there is an 8% chance that we're being a little bit unsafe and that flaw should be on the immediate dig list. And that's a problem, which I'm sure that many of you will jump up and down and shout at me for. That's okay. There's about a 4% chance that this flaw does not need to be dug at all. Now, in terms of that 8%, that's going to worry a lot of you, and I understand that. I'd like to point out, though, that right now we are talking about the safety factor that's purely associated with the model error. Right? It's very typical that pipeline operators will use a lower bound yield strength. It's very typical operators will use a lower bound toughness. It's common to use a thin wall or a minimum wall thickness when they do their safety calculations. Typically, we'll assume that all of the flaws along that pipeline are suffering the same maximum operating pressure. In effect, we're saying that those flaws are right next to the discharge station, which is not the case. When you look at all of those other conservatisms that are built into the way things are done, when you account for those, you're actually going to take this normal curve and you're going to shift it to the right effectively and improve the safety factor, not through a model, but specifically through your choice of various parameters. So although this model shows itself to have a little bit of potential for non-conservatism, I'm confident in saying that all the pipeline operators in town are going to use conservative values that will quickly and easily make up for that little gap. Now, the clear thing is for me that it's from the model perspective itself, there's good confidence in it because of the combination of accuracy and precision. Now, this particular version of the model, which I call the ELM, is a level 2 assessment, which means that you have to have the profile. That's not always going to be the case. I do have various other versions of the model. If I lump all of my 300 data together and do a gem model validation, I find that I've got an accuracy of 1.04, and I've got a standard deviation of 18%. And that's how that would look here. So in the hypothetical situation that you had an assessment point at 1.2, and that would sort of just make it onto your long dig list. Here's a situation where this particular curve predicts that there's an 8% chance that you would be non-conservative. There's a 50% chance that you would be overly conservative. But as I said, when it comes to that 8%, bear in mind that you're very, very likely to be using a minimum wall thickness and a lower bound yield strength, a lower bound toughness, various pressure, conservatism in your pressure assumptions, et cetera, et cetera. So I feel quite comfortable in reporting these numbers and knowing that there are other aspects of the pipeline integrity program that can be used to ensure the conservatism. If anybody's interested in looking at some of my other videos, you can find several on YouTube. Pipeline integrity, things that make me go, parts to 1 to 6. That's basically a critique of the NG18 equations that came out of the Patel Institute in the early 1970s. They have a very concerning length-depth issue that I think really needs to be discussed by industry. I have pipeline integrity gamma exponent model validation parts 1 to 6, which discuss the various flaw types that I've looked at in validating my model and show you where the pros and cons are in terms of accuracy and precision for different flaw types. And then I also have I've got a video which I look at stress corrosion cracking, and I find a way to determine how much crack shielding is going to affect our stress intensity factor calculations. So please help yourself to finding those. Those are all easy to find. I do actually have 3 real papers, 1 through NACE, 2 through ASME. Please feel free to poke around and find those if you're interested. The final one, a reconsideration of the log secant model for failure prediction of surface breaking flaws in pipelines. That gives you all the mathematical details of how I've derived my gamma exponent model. So help yourself to that if you're a mathematician that's interested in theory. If you've made it this far, thank you very much for your attention. I appreciate it. I hope that you followed my arguments here and that my normal curves seem to make sense and that you could follow the red, yellow, and green strategy there. When you look at this and you look at the various models that are available, you see that a lot of these models are very, very conservative, and we're not quite necessarily aware of how much conservatism is in the models. And in the long run, that can be costing some operators an enormous amount of money. So I'm inviting all integrity engineers out there to have a good think about the statistics involved in their models. And maybe you can find a way to refine your own integrity programs so that you're not spending a whole lot of money unnecessarily. That's it from me for now. Thank you very much for your attention, and have a good day.